All right, so we're going to start off by looking at second part of 4.2. Okay, we looked at the first part, which was on graphing rational functions. The last part we're going to look at is on more graphing. So the kind of problems that we did before were problems where the exponent in the top was smaller or equal to the exponent that was in the bottom. So here's a type of problem we would have done before. Let's do x squared, actually let's do x plus 1 divided by x squared minus 3x minus 5. In that case, the degree of the numerator is a 1. The degree of the denominator is a 2. The degree of the top is smaller than the bottom. That's the kind we did last week. Okay. This week, we're going to look at what happens when the degree in the top is greater than the degree in the bottom. Okay, so you don't have to write that down, but that's what we're doing. Now, when the degree in the top is bigger, the graph can start to get more complicated depending on how much bigger. We're never going to do problems that are that complicated. Okay, we're going to look at ones where the degree in the top is maybe 1 bigger than the bottom. That's not too bad. If it starts to get where the degree in the top is 2 or 3 bigger than the bottom, then that starts to get very hard to draw.
The degree is like the exponent, right?
It's the biggest exponent. So here's a problem that we would look at. The degree in the top is a 2. The degree in the bottom is a 1. So the degree in the top is definitely bigger than the bottom, but it's only bigger by 1. It's only a difference of 1. That's a 2. That's a 1. The difference is only a 1. All right, so that's the biggest one that we're ever going to have to sketch. We might look at one where maybe we had something like this. The degree in the top is still bigger, but now it's 2 bigger than the bottom, okay? Because that's a 3, that's a 1. We are not going to sketch something like that. Okay, we'll do something else with it, but we won't sketch it. All right. So first thing I'm going to show you is what's called the end behavior asymptote. In order to find this, it's something we already know how to do. Okay, it's going to use long division. And it's a little bit different than what we talked about last week in terms of end behavior model. Okay, so we mentioned something last week called an EBM. Okay, I'm going to talk about the difference between the EBM and the EBA in a little bit. Okay, so I'll get to that. And if you don't remember what the EBM was, I'll quickly just kind of summarize what it is. All right. So first of all, you only have an EBA if you have a rational function. So a rational function is a problem where you are dividing two things. What are the two things you're dividing? Depends on the problem. In the one we're going to do next, it's going to be something like that. This problem would have an EBA. We're not going to sketch it because the degrees here are 3 and 1. Okay, I told you we'd only sketch it if the one in the top was 1 bigger. Okay, that's 2 bigger, so we're not going to sketch it. Right, but this would have what's called an EBA. And the way that you find the EBA, first you have to do division. Okay. We learned how to do long division last week. We have to do that here. When you do long division, you get 2 parts to your answer. Does anybody remember what the Q stands for?
Quotient and remainder.
Quotient and remainder. When you divide it, and you get the quotient and the remainder, we don't care, listen, we don't care about the remainder. Okay, we don't care about that part at all. So all we care about is the quotient. The quotient is the EBA. So really, it's just another name for the quotient. It's something, it's not a new method. We already know how to do it. Or if you don't remember, I'll show you. But the quotient is the EBA. So there will be some problems on the test where it says find the EBA. And that just means to do the long division and write the quotient. Okay, so quotient, another name is the end behavior asymptote. So let's try an example. So this says find the quotient, find the remainder, and find the EBA, which is just the quotient. So it's really asking for the same thing twice, just making sure you know what it is. And that's going to be the problem that we do. Now, the degree in the top is how much?
The degree at the top is x to the third.
So yeah, single number, 3.
3.
Degree in the top is a 3. What's the degree in the bottom?
A 1.
It's a 1.
So you can't.
That's a difference of 2. I told you we're not going to graph it, and we're not. We're not going to graph this problem. We're just going to do what's up here, and that's all I would ask you to do on a test. Find these 3 things. Okay, so when we set up the long division, which number here goes on the outside?
X minus 2.
X minus 2 goes on the outside. And remember the numbers on the inside, if you're missing any, you need to write a 0 for the column you're missing. So we've got 2x cubed. We've got the x squared term. Do we have an x term? No, we need space for it though. So I need to write 0x. I know plus 0 doesn't change anything, but it's just there to give me a space because I'm going to need that room to do something. Yeah?
I'm confused as to why there's a plus 0x.
Why there's a plus 0x?
Yeah.
Because when you do long division, you have to have a column for every exponent from the highest to the lowest. So this is the cubed column, squared column, to the first column, and then no letter at all. If you don't make room for that, things won't line up right. Any other question on that? Some problems aren't missing it. Some problems might have it, but this one is missing the x term. So we need to say that there's 0 x's.
So say if the top one was, say if it was 2x, like to the 4th, you would need 1 for the third as well.
Yeah, if this was a 4, now you're missing the 3 as well, so you'd have to do a 0 for that one.
And you just put it in the order. You would put it like where the 3 is.
Yeah, it always has to go in order from highest to lowest. Yep. Okay, now off to the side. So this is kind of a review from last week. We're going to take 2x cubed, which maybe it'll help if I write it that way. And you're going to divide it by x. What do you get when you take 2x cubed and divide it by x?
2x squared.
Okay, we get 2x squared. And now we take that 2x squared and we're going to multiply it back out. What's 2x squared times x? 2x cubed.
Minus 4x squared.
And then that's going to be 2x squared times negative 2, which is minus 4x squared. Yep. Okay, so we multiply back out, and now we have some columns. Does anyone remember what we do with the columns? Subtract them. Yep. So we have 2x cubed minus 2x cubed.
0.
Right. Negative 4x squared minus negative 4x squared. That's going to become negative 4x squared plus 4x squared.
Is that 0?
So that cancels out as well. Okay, so we got 2 things that canceled.
So I wrote 2x squared plus 0, but the plus 0 doesn't really add anything, so I don't have to write it, or what?
So, for the next step?
I think so. Well,
So yeah, the next step, bring down the plus 0.
so why didn't you add how did that cancel out two terms? Maybe I forgot from last week.
So, because it was negative 4x squared plus 4x squared.
Yeah, but why?
It's just how the math was added up.
Yeah,
And this
but-
was 2x cubed minus 2x
No,
cubed.
no, I see that, but like on the top, like for a quotient, it says 2x squared. But why is it like?
How'd we
You
do
times
that?
into the original equation.
Like I know how we got that, but where's the number for the 4x squared? Is there no number for 4x squared where the
Negative
quotient
2
is?
times 2x to the second.
2x
Because
squared
that's
times
canceled
square root
out.
of 2 equals 4.
And because two things canceled out, that pretty much is going to end the problem. So we can bring down the next term and now take 0 times x and divide that by x. So the x's cancel, and you're left with 2x squared. You don't even have to really write plus 0.
What about the
That's what I was
three?
wondering.
Now we can bring down the 3. So we get 0. And when we bring down the 3, we can't do anything with that because that
By 3 by x.
doesn't, x can't go into it.
That'd be the remainder.
So that's my remainder.
So it's not x plus, 0 plus?
No, it would be, the quotient is 2x squared, and then the remainder is 3.
Yeah, and we're not going to write 2x squared plus 0 as my quotient. I'm just going to write 2x squared.
I gotcha.
So my quotient is 2x squared. And what's my remainder?
3.
3.
Oh, 3.
And what about the EBA?
2x
2x
squared.
2x squared. The quotient and the EBA are always the same thing. Any question how we got that? We are going to do long division more later on.
So why couldn't we have been like, oh, so I know that you can, like, because you can find the EBA just by looking at the equation, right? Because you can do 2x cubed.
Well, we had a couple things cancel out, so it did make it easier this time, but I can't always do long division in my head, especially if I don't get things that cancel out.
But it says, like, you're dividing, it's 2x cubed over x minus 2, like the whole equation, but over x minus 2. So
Yeah,
like,
and the EBA is the quotient from the long division, which can have a lot more terms than that in it.
But you didn't have to do the long division, I'm saying, because like, isn't like 2x cubed minus x is just 2x squared, or?
Well, in this case, I mean, yes, I could look at it and tell that a couple things were going to cancel, but in general,
And then you could have used the remainder theorem, and then like just factored in -2 for x.
because I mean, you could have gotten something like this, 2x squared plus 3x minus 5 as your EBA.
But,
We got lucky because a lot of things canceled out.
okay.
So I would always do the long division, like do the whole long division process. Even if you think some things are going to cancel out, great, it'll make long division faster. But the EBA can be a lot more complicated than that. Can have more terms in it. So you always want to do long division and write the quotient, and that's your EBA. Yeah.
Alright, so I was out when we did long division, but is there a reason, so I see that these two things cancel out, which makes it 0, right? And then you would do 0 plus 0x.
So yeah, these cancel out, so
Yeah,
this whole thing
so
is
it's
just 0.
And then you would add the 0x. and
Bring down my
0.
next, I could actually bring down both terms
But
at the
why
same
wouldn't you
time.
add the 3 to make it 3?
Those aren't like terms.
Oh, okay. So because.
You
but
can't
if-
combine something that has an X with something that doesn't.
You would have combined the like terms before you started the equation anyway.
Okay.
I mean, if it was 0x plus 3x, then you could say 3x,
But
but.
because as an x, you can't add it to that?
Uh-uh,
Okay.
no. And then when you get here, you're done because you can't divide x into
Okay,
3
because
because there's
there's
no
no
x.
X.
So that's just your
Okay,
remainder.
that makes more sense.
All right, and we're gonna do some more long division too. So just to kind of recap from last week, there's a difference between the EBM and the EBA in how you find them. So the EBA, that is when you do long division. The EBM, that's a lot easier. Okay, that's a faster calculation. So the EBM is when you take, let's say you had 4x cubed minus 8x squared plus 6x minus 5, and you divide by x squared minus 4x plus 12. Okay, if I wanted the EBA, then I got to do the long division. Okay, that's going to be a while. It's going to take me quite a few steps to do long division.
But the EBM would just be 4.
But yeah, the EBM, all I have to do is look at that part right there. I can ignore everything else.
And it's the EBM's the biggest, like it'd be 4x plus 3 because it's a 3 and it's bigger than the 2.
Yeah, it's the EBM is when you take the term with the biggest exponent in the top and divide by the one with the biggest exponent in the bottom. And when you simplify that, what would you be left with?
4x.
4x. That's it. That's how you find the EBM. And that was on the test, and most people did pretty well finding the EBM. So EBM is a lot easier. That's the EBM. EBA, a little different. You got to do the long division and write the quotient. Now, depending on the problem, even though there's a different way that you're finding the EBM and the EBA, they could come out the same, or they could come out different. It depends on how complicated the problem is. I don't really care if they come out the same or they come out different. You just have to know how to find each one of them. So is there any question on the difference between how you find EBM or how you find the EBA?
The EBA was just in division, right?
EBA, this is when you do the long division. And you look at the quotient.
And they stand for what again?
End behavior asymptote.
And end behavior what?
An end behavior model.
Okay. End behavior.
Okay. Two important points. I'm not worried about the third one. Because the third point, it is important, but it's not something that we're going to do. So. Okay, so now, I think I called that first problem we did example 5 because it was picking up from the notes from last week. I want to verify that this really is the EBA. Okay? And the way we're going to do that is on the calculator. All right, so what we want to do is first type in the original problem. And because it's a fraction, what am I going to need around the top and the bottom?
Parentheses over everything?
Yeah, we need parentheses around
The top and the bottom.
the top and the bottom. Yep. So we're going to put that in. That's 4x squared plus 3, and divide by x minus 2.
Can you keep that up there for a second? Oh, wait.
So I'm going to put that in y1. Let me just get a good picture for what that looks like first, and then we'll go from there.
Is there a reason you didn't put the 0x? Is that only just for solving?
When I typed it in, yeah, you don't need it. It wouldn't make a difference if you put it, but yeah, it's just for solving. Okay, so let's put that in and we'll do zoom 6. Now, before I actually look at it, I know that I can't use what number for x because it would cause me to divide by 0. 2. So we know something weird is going to happen when you get close to 2. Okay, so all of a sudden, when I get close to 2, it drops down. Let's zoom out a little bit. Let's set our Y max. Let's go to like 45. Because look at the difference between the degree in the top and the degree in the bottom. What was the degree in the top?
X squared. Well, 2x squared.
So single number. What's the degree in the top?
Oh, 3.
3. Degree in the bottom?
1.
1. That's a difference of how much? 2.
So you can't.
Think of what something at an exponent of 2 looks like. What's the shape of something that's like x squared? Like a U shape, right? It's a parabola. So when I graph this, there should be a U shape to it. What I was looking at with Zoom 6, it didn't quite look like a U shape. Okay. I set my Y max a little bit higher so I could zoom out. And tell me if you see more of the U shape now. It's not going to exactly be a U shape, but do you see kind of a U shape there?
Yeah.
Yeah. Overall, there's a big U shape. Now, it doesn't connect because it's not a parabola. But that's how you can get an idea of what it should look like. You look at the exponent in the top, it's a 3. Look in the one in the bottom, it's a 1. And if the difference is a 2, then it should look like a U shape.
Why does this matter? Like, why? No. Like, why are we graphing it to what? Like, I know we're solving. Like, we would solve and divide it to find the quotient and the EBA.
Right. So we're gonna.
Why would we graph it?
So we're gonna prove that the EBA that we found actually works.
Okay.
So we found the EBA to be 2x squared. Type in on Y2, 2x squared. If that is correct, then it should look like the graph in blue and the graph in red are getting closer to each other. Let's see what happens. Okay, so let's look at this picture. Okay, and as you look at the graph in blue and the graph in red, as you head to the left and the right, not in the middle, okay, but as you head left and right, does it look like the blue one and the red one are getting closer together?
Yes.
Definitely. On the right, the blue and red are getting closer, and then how about on the left?
Yeah.
Yeah, they're getting closer and closer. They will never reach because it's an asymptote. Asymptote means it gets closer, but it never reaches it. So what this picture shows is that the EBA that we found is correct because it looks like it's getting closer and closer.
So on a test, you would have us what? Like how would we graph this on a test? You'd be like, oh, which one shows it correct or?
So what you could do is you could graph your answer and see if the EBA looks like this.
So this is more for us, like to double check our answer.
Yeah, this is how you can double check your answer. Yep. So once you find the EBA, graph it and graph the original problem, and if it looks like they get closer and closer together, you probably found the right answer. If they don't, then you probably found the wrong answer. Yeah, so it's a way to check your answer. So use the graphing calculator to verify that that is the EBA. Yep, there we go. So any question on why that is the EBA? Okay, it's always going to do something weird in the middle, but that's not the part I care about. I care about the ends, because asymptotes only describe what happens on the ends, not in the middle. All right. Let's just try finding another EBA before we do this one. All right, so let's find the EBA. Let's do x cubed minus 2x squared plus 3x minus 4. And I'm going to try to divide into that x minus 1. Okay, so find the EBA.
Can we do this one on our own, see if we can get the answers?
Sure, you can try it and see if you can get the EBA. Remember that EBA means you're trying to find the what?
The quotient.
The quotient. So when you do the long division, we want to know the quotient. Yeah. So give that a try and see if you can find it.
What day is your late day?
Thursday.
Thursday.
Okay, so once we divide x cubed by x, what does that give me for my first term? X squared. Now take the x squared and multiply it back out. So x squared times x is x cubed. And what's x squared times negative 1? Negative x squared. And what do we do with these columns?
Subtract them.
Subtract them. X cubed minus x cubed.
0. It cancels out.
Okay, that should always happen. Now the next one, negative 2x squared minus a minus becomes a...
Plus.
So what's negative 2x squared plus 1x squared?
Is it just x squared?
No, it's just
Negative x squared.
Negative x squared. Yeah. So it's negative 2 plus 1.
Where did the minus x squared come from?
The minus x squared,
Yeah.
x squared times negative 1
Oh,
is
so you
negative
multiply
x
it by
squared.
one.
Yep, that's where the negative 1 comes in. And now bring down your next term. Now you've got negative x squared, and you're going to divide that by x.
If there's more than one term when we're putting the graph in on y equals, you do the parentheses, right?
Usually only if it's division. You will not need parentheses for the EBA.
Okay.
So what's negative x squared divided by x?
Negative x.
Negative x, yep, those cancel. Okay, multiply this back out. What's negative x times positive x? Negative x squared. And what's negative x times negative 1? 1x. And what do we do with the columns? Subtract. Negative x squared minus x squared is 0. Because that's negative x squared plus x squared. What's 3x minus 1x? 2x. And bring down your next term.
So if there's a number without an x at the end, will that always be the remainder?
In this kind of problem, yes.
Okay, because you'll never be able to have it with an x.
Correct. The remainder here will never have an x in this kind of problem.
Yeah.
Yeah, the reason that happens is really because of this right here.
So as long as there's an x in the front part, the remainder will, if there's a whole number without an x, it'll always be that.
As long as it's an x to the first, yes. If it was like an x to the second here, no.
Why?
That's another thing to talk about. It would take me a little while. Yeah. But as long as it's an x to the first, the remainder will always be a number. Okay, so now 2x. And you're going to divide that by 1x. And what do you get when you do that? 2. Now, if you're finding the EBA, you're done. If you want to keep finding the remainder, which maybe we should because there are some on the test where you need the remainder, we'd have to keep going. What's 2 times x? And what's 2 times negative 1? Negative 2. And what do we do with the columns? Subtract. 2x minus 2x is gone.
Remainder of 6.
And what's negative 4
Remainder.
Negative 2.
minus 2, which is plus 2?
Negative.
That's a negative 2. We don't need the negative 2 for this. That's the remainder. But I found it just because it's good to know how to find it in case you need it on the test. Okay, so this is my EBA. So that means when I type in the original problem, and I type that in black, my parabola in black should trace right along that other one. Okay, it should look very close. If it doesn't, then I don't have the right EBA. minus x. And notice you don't need any parentheses when you check it, because that's not a fraction. Say graph.
So I put like a wrong negative, but like mine was still pretty close, but like they weren't touching, so that shows that it wasn't right.
Yeah. So it's hard to see, but as you head to the right, can people see how the blue and the red are getting closer and closer? And then the same thing on the left. Eventually they get so close, it looks like they're right on top of each other, but they're not. They're still just barely apart. And that's how they'll remain forever, just getting closer and closer and closer and closer. Okay. So any question how that proves that what we found is the right answer? Okay. So now, let's try, I got this one, and then that's it.
We have another example of that.
I don't have another one where it has a U-shaped asymptote, but I have another one where we're going to find the asymptote and do long division. It's going to be a little bit simpler asymptote.
What's the difference? That was the.
Well, the difference in this one, okay, the last problem had a degree 3 in the top and a 1 in the bottom. That was a difference of 2. What's the degree in the top here?
2 and 1.
2 and 1, which is a difference of how much? 1. So this asymptote is going to look simpler than the other one. It's not going to be a U shape. Yeah, so it says find the EBA, and then we'll see if we can sketch this one. Because it is simpler to sketch. Okay, so what's going to go on the outside?
X minus 3.
X minus 3. And the inside?
X squared plus 4x minus 3.
Perfect. And now let's divide it and see if we get our EBA. What's x squared divided by x?
Just x.
Just x. Multiply that back out. What's x times x? That's x plus x.
Yeah, x squared.
X squared. And what's x times negative 3?
Negative 3. No, negative 3x.
Negative 3x. And we're going to take these columns and
Subtract them.
subtract them. X squared, take away x squared is gone. What's 4x minus negative 3x?
7x.
7x. And bring down your 1. Now you've got 7x divided by x.
7.
7. That's it. That's my EBA. If I keep going, I could get the remainder.
Which is 20.
But we don't, we don't need it. So any questions why I'm going to stop here? Okay, so that is my EBA, x plus 7. Okay, so now we're going to try to sketch that. Okay, to sketch that, I need graph paper. That works. I don't need graph paper, but it would be nice.
How are you going to sketch that?
So, I'm going to show you how we sketch it. So we're going to use the graphing calculator like we did last week to help us out. First thing I need to do is sketch this asymptote, x plus 7. Okay. This is not a parabola. This is like y equals mx plus b. What shape is that going to be when I draw it? It's going to be a line. It's just going to be a slanted line. Okay, it's not going to curve like x squared did. It's just going to be a slanted line. So what's my y-intercept? 7. Okay, so I need to put I'm going to bring this down a little bit.
Why is the y-intercept 7?
Why is it 7? Because it's added onto the x. So that's like the b, if this was y equals mx plus b. Okay, and then what's my slope? 1, because it's 1x. So that means up 1, right 1, up 1, right 1. And I'm just going to put this in as a dotted line right there. So my graph needs to be getting closer and closer to that dotted line as I draw it. Just like it was getting closer and closer to the parabola, it's going to get closer and closer to that. Okay, is there any number that I am not allowed to plug into the bottom?
Yeah, -7.
If you plug -7 in, the bottom would be -10. That's okay.
3.
3. You can't plug in 3. And what kind of asymptote do you get when you try to plug in a 3 right there?
Oh. You get
This is from last week.
horizontal. Oh wait.
No, not a horizontal. Vertical. Yep. So I'm just going to continue this one this way.
And you found that how again? Sorry, I was drawing the graph.
So to find the vertical asymptote,
Yep.
that's where we mentioned last week the numbers that make the denominator 0. One thing I don't like about this is I think my graph is going to be kind of up high. Oh, well, that's the way it worked out. Okay, so now to figure out what the sketch is going to look like, type it in on y equals, type in the original problem, and again make sure you use parentheses, plus 4x minus 1. And we're going to divide by x minus 3. Now, you can't plug in 3. If you go to the table and you do 3, it's going to say error, because that causes you to divide by 0. But let's pick a number really close to 3.
3.00001.
Okay, so that's just to the right, just a little bit bigger than 3, and we are up at over 20,000. So in other words, we're up very high. Way up there.
What does that mean? Like, we did that a lot last week and I just didn't understand it. Like,
It means that as I get close to this dotted line that's vertical, my y value goes up forever.
So, as you get close to 3,
Yes.
like infinity, but
As I get-
positive infinity,
As I approach 3 from the positive side, all of a sudden my y value curves straight up.
and how do you write that?
We just put a dot there, representing that it's going to go way up.
So like, how do you rate, like, as it approaches that number, or as,
I can show you, you don't need to do that in this problem.
okay, just fine.
Okay, but I can show you that, but you don't need that. Okay, so we got that. Now let's pick a number that's a little smaller than 3. 2.9999. Okay, we are at negative 19,000. So just before the number 3, you are way down here. Okay, so we know what's happening on each side. I'll do my graph in red. And again, that red dot is supposed to be up at 20,000, but that's as high as I can go. I'm at the top of my page. Okay, now let's pick a few other dots in to the left of that negative 3. Okay, because I need to start seeing what it looks like. Let's try negative 2. Negative 2, 1 is a point on the graph. So negative 2, up 1. All right, let's do some more. Let's do negative 1. Negative 1, 1. Negative 1, 1. Okay. Let's do negative 5. Trying to get an idea of what it looks like by plotting points. Negative 5, I'm at negative a half. 1, 2, 3, 4, 5, negative a half. So watch what's going to happen here. These red dots are going to get closer to that dotted line now.
I just, like, why are we graphing this?
Wouldn't it be the same if you just?
Because, like, I understand we're sketching it, but, like, why did we stop, like, when we did the, like, we found the slope, and we found, like, 3.
Yeah,
Like, I understood all that, and then you lost me at the, this extra.
So these dotted lines are just kind of boundaries that the real graph is going to get close to. These dotted lines are not the graph itself. they're asymptotes. Asymptotes are like boundaries that are going to control where the graph can go. So the graph is going to be
So we're
with
graphing the 2x plus, I mean the x squared plus 4 minus 1.
divided by x minus
Yeah.
3. Yep. We're graphing this whole thing.
I see.
And the first step to doing that is to graph the asymptotes. So
And so you typed in the equation on the y equals.
I typed that all in, what's circled in red.
Okay, and then you went to
Table.
table.
Because I'm trying to get some values that show me what the graph is going to look like.
Could you give me a second to do that real quick?
Mhm.
Just so I'm following you.
-8.
And could you move the calculator?
Okay, I'm going to do one more value. I'm just going to do when x is 1. 1, -2. That's enough red dots. I can see what's happening in this bottom section. Okay, all those red dots have to connect. So it's going to look something like this, and then it's going to keep getting closer and closer and closer to that black dotted line.
So, like when you press graph though, like it shows what you're drawing right there. So what's the point of sketching it yourself?
So we're graphing it using a table of values on the calculator because I might have you sketch something without a graphing calculator. Yeah.
Wait, so how do we find the table?
So how would
We
we?
can't use a calculator.
How yeah, I was gonna say. So how would we be using a table without a graphing calculator?
So if I had to do it without the calculator, I could type in the number 1 for x, and I'd have to do 1 squared plus 4 times 1 minus 1 divided by 1 minus 3. I'd have to plug in for x myself.
That's a lot of work.
So you'll still be able to use the table, but you're just going to have to show me the values you get when you do your sketch.
Okay, so
Yeah.
with this you're going to table.
Yep. Just saying. Yeah, so we're going to do the table.
I have a question too.
So
And then it doesn't really matter what you pick. I'm just picking several values.
How do you pick the values? Like, every time I see this, I'm never able to like add numbers. They're already there.
Second
Yep.
window, and then make sure yours looks like that. That ask means it asks me for the x value, and I can type in whatever I want.
you can type in any number.
If I put it on auto, then the calculator gives me the number.
Okay, yeah, that's what it was doing, and I was never able to type anything in. I didn't know.
Yeah, that's why. So
So you typed in for table start, you typed in 0.
I didn't do 0, but I could have. Hopefully it goes pretty close to the origin, because my sketch did. Well, it's supposed to be 0, 1/3. It's supposed to be just above it, but I'm close enough. So I've got plenty of points in here. What I need is points on the other side of 3. The problem is going to be, I think they're going to be up very high. So let's try 4. Yeah, 431. 5 is a little bit lower. It's up at 22. 6, 7. So all the points are going to be up pretty high. When you have these asymptotes and it makes like an X shape like that, it can't cross those boundaries. Okay, the dotted line is a boundary it has to stay between. So the other part of my graph has to stay very close to this line, and it also has to be getting closer and closer to that line. So the only way I can have something in that section that would do that is if it does something like that. That has to be kind of what the other section looks like. Now let's graph it and see if it works. Is that top part going to be in the standard window?
No.
No. So I'm going to set my Y max. I don't need 90, but I'm probably going to do like, I don't know, I'll do like 40. And hit graph. And let's see if it looks like what I drew. Yeah, there's the bottom part. And yeah, there's that top part. It's those two separate rounded pieces. Again, mine looks a little different because I'm zoomed out to 40 on here. That's 4 times higher than I can see on this graph. That's why it looks a little different. But there's my bottom curve going right through the origin. Yeah, pretty close to the origin, but that looks pretty good. So that's the kind of graph you would have to know how to sketch.
Both parts of it?
Yeah, and usually the X shape, it ends up being a little lower, so it doesn't go off the graph as much. But I've got another one like that we'll try too. All right, let's try. Let's try this one and see. Okay, so we changed that one a little bit just so it hopefully works out nicer. It's from the book, so I hope it does. Okay, so it says determine the end behavior asymptote, vertical asymptotes, and then make a sketch. Let's start with the vertical asymptote. That's going to be the easiest.
It'd be -2.
Yep, and since it's vertical, it's what letter by itself on the left? Yes. So we have a vertical asymptote at -2. This vertical line at -2 is not the graph. It's a boundary line the graph gets close to. Does everyone understand? Okay.
Yeah.
So let's draw in a boundary line at -2.
So is it if it's that, is it always just vertical asymptote or?
We do.
We did horizontal last week. Yes, you will not have any of these problems.
Sweet.
No. The only way it can be horizontal is if these numbers match.
Oh,
And that might be something we review later, but it's not something we're doing today. Okay, so I got the vertical. Now, how do I get the EBA?
long division.
Long division. Okay, so
So, okay, never mind.
I'm just going to try to fit it right here. So x plus 2, I'm going to divide that into x squared minus 2x plus 3. Okay, what do you get when you do x squared divided by x?
Well, X.
X, what's x times x?
X squared.
X squared. And what's x times 2?
2x.
2x. And take the columns and
Subtract.
subtract. X squared minus x squared is gone. What's -2x minus 2x?
0. Or, no.
4x. -4x.
Yeah.
-4x. And you can break down the 3, but it doesn't matter because it's going to be the remainder. What's -4x
-4 would be -4.
divided by x?
Would it just be -4?
Yep. Okay, I think that's going to work out a lot better for the asymptote. Okay, any question why I don't need to go any further? That's my EBA. X minus 4. Okay, what's the y-intercept of that?
4.
Yep, no, not 4. -4. And what's my slope? 1, which means I go which way when I graph that?
Up and to the right.
Up 1, right. Okay, again, this is not the graph. These are boundary lines that the graph is going to stay between. Okay, so now we're going to pick some points. I wouldn't go beyond -10 and 10 because my graph paper is only that big. So type in the original problem, which was, actually I can see it, x squared minus 2x plus 3, and the bottom was x plus 2. Okay, there's already some values in there. You can just keep them, or you can get rid of them. It doesn't matter. Look at what was the vertical asymptote?
It was -2.
Okay, let's pick a number that's a little bit smaller. What's just to the left of -2? A number a little smaller than -2.
Well, a negative 1.99999.
Well, we need to do that one too. That's bigger because that's to the right of it. But we can do that one too. So that's bigger than -2.
-0.
So that means we're up at 10,000. So when you are just to the right of -2, you are way up here. I already have an idea of what's going to happen in that section, because it always has that shape. Okay. How about a value that's a little bit smaller than -2?
-2.0021.
Yep. And we are way down at a huge negative number. It's over -100,000. It says -2, but it's not. It just rounded it. Okay, so we are way down here. Okay, so now we just need a few more points. Let's do this bottom section first. Let's do let's try -3. And hopefully that's on the graph. Nope. -4. Okay, that's kind of close to the graph. So -4, we're down 13.5. So let's go -1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say 13.5 is about right there. So remember, these are going to be boundaries. This keeps going. This keeps going. Eventually, it has to start getting very close to that one, and it has to get very close to that one. So that section is going to do something like that. As you continue to the left, those red one and the black one are going to get closer and closer, just like the parabola. Okay, a little hard to sketch it because it went off the graph, but I think we got it. What would be a good x value to pick to see what's going on in this other section? 5? Yep, we could do 5. So 5, 2.5 roughly. 1, 2, 3, 4, 5. 1, 2.5. Okay, so there's another one. What would be another good x value? 3? We could do 3. 3, 1.2. 1, 2, 3, 1.2. All right, how about another one?
-1.
I heard 0. Sure, that's a good one. 0, 1.5. Right. So I got enough points to see. All those red dots have to connect. So it's going to come down. It's going to curve. And then as you head this way, it's going to keep getting closer and closer. Okay. And that's what it would look like. If you go to your window and set your y min at like probably -30, and you could probably keep that at 15, I think you'll see an okay. Yep, so there's the bottom part, and then there's the top part. And if you type in the EVA, you can check it and make sure that it looks like it's getting closer and closer. Let's see. Does it look like the blue and the red line are getting closer and closer? Yeah, they're going to keep getting closer and closer. So that confirms that what we found is the right answer. Any question on that? So that particular asymptote that we just found, that is called a slant asymptote. And so was the last one. Whenever you have a line that's on a diagonal, that's a slant asymptote. So on the test, if I ask you to find a slant asymptote, it's what we just did in that problem.
So it's both of those asymptotes together?
Yep.
It's a slant asymptote?
That was a slant, and that other one was also a
So
slant.
the EBA and the vertical asymptote is the slant asymptote?
Well, no, the vertical asymptote is a vertical asymptote.
But then together is the slant, or,
The slant is just the one that's on the slant.
so the EBA is
The
the
EBA,
slant?
yes. The EBA is the slant. In this one that we did, this does not have a slant asymptote. The red one curved. That was not a slant.
So EBA.
The EBA is the slant. And the vertical one, that's
Just the
separate.
vertical.
That's just the vertical. Yep. So determine the EBA and the vertical, and that's what we did. EBA and vertical. But they're separate. Okay, let's finish up by graphing this one. Now, this one, too complicated to graph by hand, so they tell you to just use a calculator and graph it. Okay, what do I need when I type it in?
Parentheses.
Yes. So we're going to do 2x to the fourth plus 7x cubed plus 7x squared plus 2x. And we're going to divide that by x cubed minus x plus 50. Other than the parentheses, you can type it in exactly like what you see right there. All right, I just want to graph it and see what it looks like. Because I think something's going to happen in this graph that I might have to zoom in to see a little bit better. Let's do zoom 6. See if that's a good window. Okay, well there's a bottom piece and there's a top piece. So it kind of looks like the ones we've been doing. I'm going to set my Ymax higher. Set your Ymax to like 30. So there's the bottom piece, and there's the top piece. What kind of asymptote does it look like this problem has that we talked about today?
A slant?
Yeah, there is a slant. I don't know exactly where because I'm not finding that, but it's probably not like that. It's probably like somewhere in there.
What makes you say that?
Just because I can tell if I put this like right about there. I didn't zoom out quite enough, but I know if I zoomed out a little more, this top piece is going to eventually go like this. And it's going to curve back down just a little bit. And then the green and the blue are going to get closer together that way. And they're also going to get closer together that way, just like that. So it does have a slant asymptote. Okay, but looking at that graph, does anybody notice anything there that we might need to check out a little closer?
The bottom piece?
Yeah, well, the bottom piece is pretty much just going to go like this, and that's just going to go like that. So if you zoom out a little, you'll see that on the bottom.
There's like a little.
Yeah, the x-axis. I would check out what's happening there. Because one thing we want to be able to tell is, does it cross the x-axis? Right now, I can't really tell.
Why do you want to see if it crosses the x-axis?
Because sometimes they might ask you for the roots. And unless you can see if it crosses the x-axis, you can't find the roots. And I can't tell looking at that. It just looks very flat. So what could I do for a y min and a y max to zoom in on that section? Pretty much right where I drew the blue box.
I have no idea.
Could it be like 4?
Well, where does it look like my box crosses the y-axis?
1.
Yes.
1, and well, I made it a little lower than I needed to, but I could do 1 to,
1 to -2.
yeah, I mean 1 to -1 I think would be okay. So let's do -1 to 1 and zoom in on, we're basically going to zoom in on that blue box. Now, how far left does that go? My blue box.
3, 4.
Well, that positive would be to the right. So I agree, it goes to the right 1 and left negative, I would do -1, -3 is right there.
Yeah.
So I would do -3 to 1. And let's zoom in just on that box and see what it looks like. So what do we think? Does it look like it crosses the x-axis, or can we still not really tell?
It looks like it crosses the x-axis a little bit.
For me, I don't know if it's just my calculator, but like it goes down and then there's like a little piece underneath and then there's nothing and then it goes up. Like it looks like there's a gap in it.
I'll take a look at that after. Let me see it. Okay, so can we see clearly how many times it crosses?
No.
No, let's zoom in even more. Let's zoom in on a box like right there. So what could I do for a y min and max this time?
-2 instead of -3.
Well, I'm already at -1 to 1, but I want to zoom in a lot more on the y-axis.
0.5.
0.5, I'm going to go even more. I'm going to go like -0.1 to +0.1. So I'm very zoomed in on the y-axis. And let's look at what that section looks like in that box when we zoom in.
It's weird.
What do you notice now?
It goes up and down.
Yeah, it's what we originally thought looked very flat because we were zoomed out. What I'm trying to show you is it doesn't look flat at all when you zoom in.
And it goes back.
Yeah, and let's see how many times it looks like it crosses.
Twice. But when you zoom in, it just keeps going.
Okay, so look at that carefully. How many times does it look like
Twice.
that crosses?
4.
Oh, yeah.
Yeah, when you zoom in, at least to this point, it looks like it crosses 1, 2, 3, and 4. So the point of that problem is something that you might look at when you're zoomed way out looks flat. When you zoom in, it's not really flat at all.
How would you ever think to like zoom in on that? Because like I don't know, I would have just left it like that.
Well, if they're asking you to calculate where it crosses the x-axis, then you have to zoom in because that's what the question's asking you to do.
I was like, you just like were curious.
Yeah, no, it would ask you to like find the roots.
Okay.
But I can't find them with the big window. I would have to zoom in like that. Now I can find them.
What causes it to like ripple like that?
Just because there's so many different terms in it.
Okay.
That's a lot of terms, so the more terms you have, the more complicated it can start to look. Yeah. Okay, so any question, that's called hidden behavior. It's something that's not obvious to see, but if you zoom in, it's very obvious. All right, so that is the homework for tonight. So on page 235, 37, 38, 41, and then 45, 46, 48, and 55.
And this is unit 4.
This is 4.2.
Okay.
So it's in the 4.2 lesson.
Yeah, that's just what I read, so I know it's 4.
Okay, so we will take a look at that tomorrow. And then tomorrow will be our last lesson for this week, which is in graph and law. So no graph.